Hello everyone and welcome back to my YouTube channel. Today we will discuss electronic configuration of elements for class +1 under the chapter atomic structure. So what is this electronic configuration? Electronic configuration refers to distribution of electrons in atomic orbitals. It refers to distribution of electrons in atomic orbitals. For example, I have atomic number 2, helium. How to write its electronic configuration? That is 1s2. 1 represent principal quantum number, means shell number. S represent subshell, and these 2 represents 2 electrons are present in one orbital. That is the basic notation of electronic configuration. 1s2 for helium. Easy. There are some rules for electronic configuration. Let's understand each and every one. First is FUBA principle. Actual FUBA words comes from a German word, and its meaning is building up. FUBA words mean building up. There is a building up of orbitals, and according to principle, FUBA principle, electrons are arranged in orbitals in increasing order of their energy. Electrons are arranged in orbitals in increasing order of their energy. Means electron will occupy the space in a lower energy orbital first. Electrons will occupy the space in a lower energy orbital first. That is the FUBA principle. And how to find out which orbital have least energy, which has highest energy? For that we have one more rule, that is N plus L rule. Second is N plus L rule. N is a principal quantum number, L is a azimuthal quantum number. The sum of the principal quantum number and azimuthal quantum number. According to this rule, electrons will enter in that orbital first whose N plus L value is least. Electron will enter in that orbital first whose N plus L value is least. By finding the N plus L values, we can represent the electronic configuration sequence of elements. Easy. Let's draw a table for N plus L rule, so we can find out the correct order of atomic orbitals for filling up the electrons in orbitals. Easy. N is a principal quantum and L is a azimuthal quantum number. Here we have N and here we have L. L0, L1, L2, L3, so on. For value 0 we have the subshell S subshell, for 1 we have P subshell, for 2 we have a D subshell, for 3 we have a F subshell, for 4 we have G, and for 5 we have a H. Easy. So if N is 1, if N is 1, then subshell is 1s, first shell contain only one subshell. For N equal to 2, subshells are 2s and 2p. For N equal to 3, subshells are 3s, 3p, 3d. We have understand it in a previous lecture. N equal to 4, we have 4s, 4p, 4d, and 4f, 4s, 4p, 4d, and 4f. Easy. Next, N equal to 5. The possible values of L are 5s, 5p, 5d, 5f, and 5g. N equal to 6, 6s, 6p, 6d, 6f, 6g, and in here we have another orbital 6h. And for 7, possible values are 7s, 7p, 7d, 7f, 7g, 7h, and 7i. 6. Easy. So in periodic table we have a 7 period, and for 7 period 1 to 7 we have these orbitals. And what is the rule? N plus L rule. The minimum value of N plus L, that orbital will contain electrons first, or electrons will enter in that orbital whose N plus L value is least. Let's add the value of N plus L. For this we have 1 plus 0, 1. Here we have 2 plus 0, here 2 plus 1, 3, 3 plus 0, 3, 3 plus 1, 4, 3d, 3 plus 2, 5. Again here 4, 4 plus 1, 5, 4 plus 2, 6, 4 plus 3, 7. For F, value of L is 3. 5, 5 plus 1, 6, 5 plus 2, 7, 5 plus 3, 8, and 5 plus 4, 9. Easy. Here 6, 6 plus 1, 7, 6 plus 2, 8, 6 plus 3, 9, 6 plus 4, 10, and 6 plus 5, 6 plus 5, here we have 11. Easy. 7, principal quantum number 7, shell number 7, 7, 7 plus 1, 8, 7 plus 2, 9, 7 plus 3, 10, and 7 plus 4, 11, 7 plus 5, 12, and 7 plus 3, 13. So for these orbitals we have the value of N plus L. So now what we have to do, we have to find out the least value. First least value is 1, so electron will enter in 1 as first shell, and S is a subshell. So electron will enter in first 1s. Next least value is 2, electron will enter in 2s. Next value is 3. Here we have two orbitals for a n plus L value 3, 2p and 3s. If value is here same, then what we have to do, we have to find out the least value of n. Here n is 2 and here n is 3, so electron will enter in 2s after 2p. From after filling the 2s, we will fill the electron in 2p. From 2p to 3s. Again we have for value 4 we have two orbitals 3p and 4s, but for this n is least, 3 comes first, then 4. So after 3s electron will enter in 3p. From 3p electron will enter in 4s. Now for 5 value we have 3 orbitals 3d, 4p and 5s. 3d, 4p and 5s. So least value of n is 3. So after filling 4s orbitals, electron will enter in 3d orbitals. From 3d it will comes to 4p. From 4p to 5s. So now we have the orbitals arranging in their increasing order of energy. 1s, 2s, 2p, 3s, 3p. From 3p, 4s, 4s, 3d, 4p and 5s. Next value is 6. For 6 again we have 3 orbitals 4d, 5p and 6s. So for this value of n is smaller, 4, 5 and 6. So electron will enter in 4d first. From 5s to 4d, 5p and here become 6s. Next value is 7. 1, 2, 3, 4. For 7 we have 4 orbitals 4f, 5d, 6p and 7s. So definitely n is smaller here. So from 6s we will fill electrons in 4f orbital. From 4f to 5d, 5d to 6p, 6p to 7s. Easy. This is the sequence of orbitals in their increasing order of energy. Next value is 8. So if we have 8 period number, then orbital will be 8s and value is 8. From if we move from 7, for 8 we have 4 orbitals 1, 2, 3, 4, 5f, 6d, 7p and 8s. So definitely again we can see n is smaller here, 5, next 6, next 7 and next 8. So from 7s electron will fill in 5f orbital. After filling 5f orbital we will move to 6d and from 6d to 7p and then we will come to 8th shell or 8th period number, that is 8s. And again we can solve for 9, but in periodic table we have only 118 elements. In periodic table we have 118 elements and 118 elements are filled in 7p. From 1s to 7p 118 elements are filled. Easy. So now I am going to represent the increasing order of atomic orbitals. As we know, one orbital contains 2 electrons. So first electron will go to 1s2, next 2s2, next 2p6. Why 6? Because p subshell contains 3 orbitals. So electron total will be 6. 2p6, next 3s2, next is 3p6. From 3p6 we come to 4s2. After 4s we have filled 3d, and d contains 5 orbitals, so total number of electron will be 10, 3d 10. From 3d, next is 4p6, next is 5s2. From 5s2 we have moved to 4d 10, next is 5p6, next is 6s2, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. From 6s2 we move to 4f14. Why 14? Because f contain 7 orbitals, so 7 into 2, total electrons will be 14. 4f14, next is 5d10, next is 6p6, next is 7s2. From 7s2 we move to 5f14, next 6d10, next is 7p6. This is the correct and right sequence of atomic orbitals in increasing energy. Electron will enter in those orbitals first whose n plus l value is least. So electronic configuration starts from 1s2 and we have ended here 7p6. If we total count the electrons, then total electrons here will be 8 electrons. Clear? You don't need to cram it, you can simply practice at home by arranging them and by finding the n plus l value. This is the second rule, n plus l rule. Clear? Let's do some examples first, then we will move to third rule. So here we have the increasing order of atomic orbitals. Let's solve some examples. For example, we have to write the atomic number 17, that is chlorine. What is the electronic configuration of chlorine? So just count the electron. We need 17 electrons. 1s2, 2s2, 2p6, 3s2. How many electrons are filled? 10, 12. We need 5 more, then 3p5. This is the electronic configuration of chlorine. Here we can use electronic configuration with respect to noble gases also. 1s2, 2s2, 2p10. I think 10 electrons are there and 10 electrons are present in neon. So this is the noble gas configuration, 1s2, 2s2, 2p6. So we can short it neon, 3s2, 3p5. So electronic configuration can be written with respect to the nearest noble gas. Simple. Next, for example, we have to write the electronic configuration of sodium. Atomic number 11. So we need 11 electrons. From here we can see 1s2, 2s2, 2p6 is the configuration of neon, and atomic number 10 means 10 electrons. So I can write it simply neon. Next electron will enter in 3s1. Just count the electron and fill it, so you can write the electronic configuration of elements. Clear? One more example. For example, we have to write the electronic configuration of scandium, atomic number 21. First complete configuration, 1s2, 2s2, 2p6, 3s2, 3p6. We can see 18 electrons are filled, 2, 2, 4, 10, 12 and 18. We need 3 more electrons. So after 3p6 we comes to 4s2. Now electrons are 20. Next is 3d10. So first electron will come in 3d1. This is the electronic configuration of scandium, we can write with respect to nearest noble gas. That noble gas is 18 electrons. Atomic number 18 is argon, 4s2 3d 1. So if you know the correct sequence of atomic orbitals in their increasing energy, then you can simply write the electronic configuration of elements. Clear? You can practice at home. Next rule is Hund's rule. First was FUA, second is N plus L, third is Hund's rule. This rule explained the pairing of electrons in orbitals. This rule explained the pairing of electrons in orbitals. According to Hund's rule, Hund's electron can pair up if there is no vacant orbital. Electron can pair up if there is no vacant orbital, or we can say alternately, electrons are filled in every orbital and then after pairing start. Let's understand with the example. For example, atomic number of carbon is 6. So its configuration will be 1s2, 2s2, 2p2. Now I am going to represent this configuration in orbitals. S contain one orbital, this is 1s2, this is 2s2, and P contains 3 orbitals. P contains 3 orbitals. So if I fill electron like this, both electrons are in a first orbital. This is a wrong representation, wrong notation. How electron will be represented? 1s2, 2s2, and we have 3 orbitals, so 2 electrons will enter in a single orbital, 2p2. This is the correct. Clear? So pairing starts when there is no vacant orbital, or after filling the all orbitals with one electron, we can pair up. Clear? Let's do one more example. For example, I have configuration D6. I have to fill 6 electrons in d orbitals. So for d subshell we have 5 orbitals. So if I fill electrons like this, 1 2 3 4 5 6, wrong representation. Why? Because there is a vacant orbital. And if I fill like this, 1 2 3 4 5 6, again wrong. Why? Because 2 orbitals are vacant, empty. So D6 will be represented as 1 2 3 4 5 6. This is a correct representation of D6. Simple. For example, I have to fill P4, 4 electrons in p orbitals. So correct will be first 3 electrons will enter in 1 orbital. Now pairing can be possible because there is no vacant orbital. So P4 will be this. If we have to represent F8, 8 electrons in F subshell, F contain 7 orbitals. So 8 electrons will be like filled 1 2 3 4 5 6 7 and 8. So pairing is possible when there is no vacant orbital. If there is a vacant orbital and we paired up, that will be the wrong representation, wrong electronic configuration. Clear? This is the third rule, Hund's rule of pairing. Fourth rule is Pauli's exclusion principle. Fourth is Pauli exclusion principle. What Pauli concluded, that he said that it is not possible for any set of electrons to have all the 4 quantum number same. It is not possible for any set of electrons to have all the 4 quantum number values same. Or alternately we can say one orbital can contain 2 electrons with the opposite spin. One is clockwise spin and other is anti-clockwise spin. Clockwise spin we have represented with the positive sign, positive half, and negative we have represented with the anti-clockwise we represented minus half. Let's solve it again. For example, we have electronic configuration 1s2. So 1s2 contains 2 electrons, value of n, L, M and S, and principal L azimuthal, M magnetic and S spin quantum number. For example, we have 2 electrons. For first electron, N same 1, L S subshell, so 0, S contain 1 orbital, 0, spin is clockwise. For second electron, it was for first electron N1, L0, M0, but now spin is different, so positive half is replaced by negative half. So it is not possible for any set of electron to have all the 4 quantum number values same. One value must be different, that is spin quantum number value for any set of electron will be different. Easy? So these are the 4 rules used to write the electronic configuration. First was principal quantum number, second azimuthal quantum number, third Hund's rule, fourth is Pauli exclusion principle. That's it for electronic configuration. In next lecture we will solve some exceptional electronic configuration of D block elements, means transition elements. Later on you will realize it. Stay at home, keep learning, and do a favor, if you still didn't subscribe my channel, subscribe it. Thanks for watching. Bye bye.